Thank you. Thank you, Cindy. Hey, I mean, this is amazing. I mean, I never thought, like, when I was a postdoc and a graduate student, there were a couple of the little motley crew of us, and we would, I don't know, go to cafes and maybe pubs and things. This is not being recorded. And I don't think any of us ever presumed that any of us would end up as professors anywhere. We're looking at one of them there, my buddy Damien, where we did our PhD together with the same advisor and wrote papers in Vancouver and other places. And he was Rhode Island state champion in pool. Did he tell you that? Okay. So you see what he spent his senior year. Anyway, it's a great pleasure to be here. And it's also a great honor to be with Paul Davies, because I read his books when I was a student. And so that's also a great honor and inspired me to write books myself. So is there a way I can advance slides? Oh, is this it? Is this thing here? No. Okay, but the space bar, right? And the arrow does it. Okay, yeah, okay.
The arrow should also
All right.
yes.
So, yeah, all right, let me just get myself settled in. I have a 2-hour jet lag. Those things matter to me. What I'm going to try to do is to kind of put you in the mind of what we call, what an experimentalist call a theoretical dreamer. Humphrey Maris, remember Humphrey Maris? And Anthony, get downstairs to the lab. Stop hanging with these theoretical dreamers. I remember that line. Okay. Meaning that we work hard, we spend many years doing things, and at some point we have to pay the piper and construct a nice narrative. This is a narrative of how, as a particle cosmologist, I want to attempt, or how I've attempted to address some long-standing problems in my career, along with my other mates along this journey. And to do this, since I'm in an audience of smart people, there will be jargon that I'll try to minimize, of course. There will be some slides with some equations to actually show you that I actually calculate from time to time. But the most important part of my talk is just to make sure that there's some kind of coherent narrative in physics story. So that's kind of my warning to you, that hopefully you'll be able to get 75% of my talk, all right? Okay. Also, another warning, I may not get through all of my talk, so I might skip slides, okay? And if that's the case, you can always email me and I'll tell you the rest of the story. So first I wanna acknowledge my students. So Leah Jenks, she just finished up last year. She's now at the University of Chicago as a postdoc with Wayne Hu. Michael just got a postdoc at MIT. Tats is his third year. He came from MIT. Alejandra actually transferred to UC Santa Cruz to do real astrophysics, but she was watching her master's with me. And Lawrence just joined me from UC Berkeley as an undergraduate. So I want to couch my talk with some questions here. So there are 3 mysteries, and certainly there are many mysteries. I just learned about some by talking to Cindy this morning, earlier on. And the mysteries I want to talk about today is, what is the origin of cosmic structure? What is the identity of dark matter? What is its character? We know it exists, but what is its identity? How does it fit in to the rest of known physics? Why is there more matter than antimatter, what we sometimes call this baryogenesis? And of course, what I want to, I don't know what the word is, what's the word? Con you into wondering is, are these mysteries pointing to a common cause? Now, since I'm amongst friends here, okay, let's pretend that there were no theories beyond the standard model. And so I want to say that, what do we know in terms of theory that agrees with experiment? Well, modulo a dark sector, and maybe that general relativity is the correct theory of gravity in the strong and weak gravitational regimes. And we also know up to the scale that we've gone at the Large Hadron Collider, detecting the Higgs, that the standard model is the correct theory of the other three interactions as an effective field theory. That's what we know. Anything beyond that, of course, is why we get paid to do what we do. But this is what we know. And the reason why I want to start from there is to say, let's go back to what Albert Einstein really taught us. He said, well, a way to really think about physics, think about science is maybe through the lens of principles. So he has a notion of principle theories. And in my second book, I talk about this. I have a whole chapter about Einstein and how he was able to, before jumping into any mathematical equations, just really think about the principles. So if we look at these two theories that we know well, general relativity and the standard model, there are two principles really underlying these theories. I mean, in both cases, actually, the things that GR, so what I'm actually doing now is I'm going to compare what GR and the standard model general have in common and what they don't have in common, okay, and ask a question about that. So they both enjoy symmetry principles. The symmetry principles function differently in both theories, right? In general relativity, we have this equivalence principle and invariance under general coordinate transformations, and physics remaining the same. And here there's a symmetry principle that we call local gauge invariance, but it's still a symmetry principle. But they're different in that the standard model is chiral, and I'll talk about that in the next slide, and general relativity is not chiral. So they're similar as theories in that sense, but the standard model is chiral and GR is not. So I'll say more about that. And my jump off point from what we know to what we don't know in terms of addressing these three questions is to say, maybe if we try to make GR closer to the standard model in this way by making it chiral, does it address any of these three questions? So that's my thing. So normally this would be an animation, and the animation would have had these vectors rotating as a vector field propagating along this direction as if other components of this vector field is rotating, and that would be a circularly polarized wave, right? So that's basically an example of something that's chiral, which is that as it propagates, it circulates in some kind of helical sense. And it is chiral in the sense that if I reflect this in an image, in a mirror, right, it does not superimpose. So the reflected image cannot superimpose to give you the same object. So same as my right and left hand. It's like this is chiral in the sense that if I do a parity transformation, if I reflect along a two-dimensional plane, right, this image is not the same. It's not superimposed. Objects that are perfectly achiral are objects that if I do a mirror reflection, like a ball, right, I can superimpose it and it looks the same. So waves can be chiral, but also matter can be chiral. So for example, an electron or a neutrino is a better example because they move at, if it's massless, that if it's spinning, like this wave spinning, right, and the sense of handedness is another way I like to do this. If I throw a football, okay, I'm being American centric here, okay, not a soccer ball. If I throw a football with my right hand and it spins as it goes towards you, that's right-handed, right chirality. If I throw the same football with my left hand and it spins in the opposite direction, but moving in the same direction, they have right opposite chiralities. So why is this important? Because there's a very beautiful link between parity violation and chirality. And this is, let me just make sure I pin this down. So not too long ago, I don't know, 4 decades ago, maybe. Oh, yeah.
I can go right off the screen over there.
Yeah, there's this way to do it. I always forget. There it goes. All right, good. So ignore this other side for now, okay? But anyway, that's like a George Lakoff statement, right? Don't think of an elephant. All right, so we're looking at the fundamental process of inverse beta decay, which is the root of parity violation in the weak interactions. And in a nutshell, experimentalists went looking for this when theorists did not want them to do it. The theorists were like, they were not going to expect parity violation because they had theoretical prejudices. Experimentalists went anyway, and they found that parity was violated, they found it was violated maximally. And now let me talk about what that means. So just same way I talked about a chiral left-handed W boson that is mediating the transition of a up quark to a down quark. It emits a W boson that's left-handed and left and right-handed electron neutrino states. If I go looking for a right-handed W boson emitting a right-handed lepton and quark, this 100% does not reveal itself in experiments. So the other chiral state of the standard model does not exist, and therefore we say that that theory is maximally parity violated. So the weak interaction violates parity because it is chiral. If there was no chiral interaction to begin with, I can't speak about parity violation, right? Left-handed states only couple to left-handed states. Right-handed states only couple to right-handed states. That's a statement of chirality. Parity violation inverts those two things, and we don't see that inversion experimentally. And that's important for what I'm going to talk about next. The question is, now I'm going to ask you, general relativity does not, if you look at the structure of the Einstein field equations, the same way we have photons and W bosons and gluons. In general relativity, we have gravitons and gravitational waves, its classical counterparts. And the statement that the general relativity is achiral means that left and right-handed gravitational waves could care less. Okay, it couples to everything. Okay, so another way of saying this is that if I look at vacuum solutions of general relativity in its ground state, it produces just as much left-handed gravitational waves as it does right-handed gravitational waves. So this is where GR and the standard model really do differ. They differ on other fronts, but by focusing on this, by the way, this would be a nice way, I think, for the double copy people to think about, right? Anyway, this is a nice way to now talk about what I'm going to talk about, if this works. Okay. It doesn't like chirality, this computer. All right. Okay, I will use the mouse. So now I'm going to go from the microscopic to the macroscopic. And now go into the realm where we want to talk now about our problems. What we're going to do now is journey into structure formation and talk about our best theories about how we think about the origins of structure formation. Oh, you know, we learned a lot about that in that yellow book called by Burrell and Davies. Since some of these things come from a vacuum named after him. And so what we're looking at here is I believe this is the Planck satellite. In a nutshell, these these undulations of different colors corresponds to ripples in a baryon photon fluid on the order of 3,000 degrees Kelvin, about of redshift 1100. So basically, as we go back about 13.8 billion years in the past, the universe was hot and dense, and it was in a state of a very tightly coupled plasma of photons and electrons. And there are these ripples, and it appears very chaotic and structureless. And the name of the game, of course, is to realize that these tiny undulations, 10,000ths above the average temperature, which is 3 degrees Kelvin today, that these fluctuations are the things that grow into forming the first structures in the universe the stars and the galaxies, and of course, us. And we just, this is the money slide that every cosmologist will show, is that here's the past, here's the CMB, these fluctuations grow into the large-scale arrangements of large-scale structure. Real astrophysicists actually study the galaxy distributions on large scale and compare the distribution of galaxies, the statistics, something called the matter power spectrum, to the CMB, and we get beautiful agreement. This is very nonlinear stuff, nonlinear gravitational physics. This is very linear quantum stuff, right? And we have a beautiful picture. Obviously, for these things to happen, we need things like dark energy and dark matter to make the game more coherent. But this is the story of structure formation. So when I talk about structure formation, I'm going to talk about the fluctuations in the CMB, the cosmic microwave background radiation. Am I going too fast in my language? Oh, I'm going backwards now. Oh. Okay. So how do we understand this physics? And so in the 70s, Peebles and you, and there was some other people, I think it was Zeldovich, before the CMB existed, before this data was taken in the early 90s by the Kobe satellite, study the fluctuations of the cosmic microwave background. In the 70s, Jim Peebles did a calculation where he took the Einstein field equations and an expanded background, considered fluctuations, considered the spectrum of these fluctuations, and got a curve. I'll show you the curve in the next slide. But his genius, and I think he got the Nobel Prize for this, was to understand the correct physics behind these fluctuations. And that physics is a physics of sound. So this plasma, right, is a medium by definition that carries sound waves. If it carries sound waves, then that medium, its existence, you can imagine it's some kind of an instrument. So if I excite an instrument like this flute, and I play one note out of this flute, so this is actually a spectrum, a power spectrum on the x-axis. This is frequency on the y-axis. It is the loudness in decibel or the power or the amplitude of the note. And I play one note. In this case, the note is a G. It goes like da. I have perfect relative pitch. So that's actually an A. So I play a G. But what happens is that this instrument excites a spectrum of frequencies. But you hear the A. And so that would be the one that's the feature that's, of course, the frequency that's the loudest has the highest peak. But then you'll have like some kind of decay of other frequencies that you hear as what makes a flute sound like a flute. Its signature, its color, its timbre. If a clarinet were to play the same note, it would have a different spectrum here. And so what is that doing? Those other peaks, it reveals the material makeup of the instrument. If it's metal, if it's an alloy, if it's wood, what have you. It also reveals the geometry of the instrument. So you can actually reconstruct knowing what this instrument by knowing this spectrum. You can reconstruct its geometry and its material, some information about its material makeup, and also, the fact that there's a harmonic, the first fundamental harmonic. And so that's exactly what we see with the CMB. We see its spectrum, if I compare the different sizes of waves in this data, you'll see basically a resonance, which will be the note that you hear the loudest. That will give me the information about the size of the universe, the horizon. And these other peaks will actually give me information about how many neutrinos, photons, and dark matter that's necessary for the instrument. So the physics of instruments, it actually maps very nicely into how we think about the CMB. So this solid curve here is Jim Peebles' theoretical prediction and these best fit on 5 parameters. and these dots correspond to the data. All right, and this down here is the CMB also makes a prediction about the polarization of light, and this is the E polarization that's also modulo, some anomalies down here agreed with the data. All right, so our picture of structure formation, meaning that something in the early universe that I haven't yet told you about, that's operational in terms of general relativity, because remember, for this to work, you need space-time to expand as well as these fluctuations. And I want to talk about that, because what we're going to do is we're going to take this picture about how structure formation happens to produce the CMB, and modify it to include chirality. So I'm going to talk a little bit about cosmic inflation. And in a nutshell, one way you can imagine, again, this picture of cosmic inflation is that there's some field, we think it's something like a spin zero field. We call it the inflaton field. We've all written papers about inflation. I think the only idea of inflation I think that's robust is a Bunch-Davies vacuum. Okay, but the point here is that there is some epoch in the very early universe that could occur anywhere from the Planck scale to the Guts scale, where the universe is actually dominated by some vacuum energy contained in this field called the inflaton field. And the energy density in this inflaton field drives space-time to expand very exponentially. And it's this exponential expansion that's acting as a quantum squeezing for the quantum fluctuations to actually imprint itself as the origins of the structure in the universe. And that's a bit of a weird picture. And now let me give you a quantum field theorist way of thinking about this. And the quantum field theorist way of thinking about this is an interesting trick, which is that the photon self-energy diagram. So here's a photon, here's an electron-positron pair. This is the Lamb shift. This has been experimentally observed, right? Was it 51 megahertz correction? So anyway, this Lamb shift is we have a virtual pair creation. So if this was some delta t, right, this happens at a delta t so tiny that we never see this effect directly, that these electron-positron pairs never become real. They're very short-lived. But inflation manages to trick us. What inflation does for us, it can take a virtual process that gets created, but by the time before inflation ends, it can get realized as density perturbations because the delta t is so tiny during inflation. By the time this delta t happens, these particles leave the horizon. So this is a curved space-time version of how inflation does its trickery, how it can take quantum fluctuations and make them real. But now I leave for you a puzzle, because as I said, if all we had accessible to us in my world was the standard model, the vacuum of the standard model has equal amounts of matter and antimatter. So if I use these virtual processes and I create matter and antimatter and they come realized now, they can annihilate and I'm left with nothing. So at some point, as I'm forming my structure, during inflation, after inflation, if I don't have a way to bias matter over antimatter, right, then it's as if I've created nothing to begin with. So something has to happen to basically create the asymmetry between the matter and the antimatter. And there is, in the theory business, where we work on these things, I'm sure some of us in the room have thought about this a lot. There's a question and there's some wiggle room as to when that happens. since he loves the electroweak theory and has worked on particle things called spherons, know that it is a one bit of physics that we can count on to at least generate some kind of baryon asymmetry. And every model I know of, and I'll say more about this, relies on that. You rely on this, so we have the electroweak theory that's operating on the scale of, say, TeV scale. So we have from inflation to that scale to do the job, to make sure that my matter and my antimatter are biased. And so the game I'm going to play now is to let inflation do the job. Let inflation do the biasing. So in other words, since we are using inflation to actually generate the seeds of structure, why not have inflation? We can ask, do the biasing to produce more matter over antimatter. All right, so I want to be very clear about the game that I'm playing, right? Because what's the best way to say it? It ain't no joke. There was a rap song that would say, it ain't no joke, whatever. Well, I guess the computer doesn't like my joke. Okay. So how do we do this? How are we going to go about doing this? So let me just give away something. This is a metric of space-time. There's a part of the metric that makes a space, and the homogeneous part that makes the space-time stretch. There's a part of the space-time that encodes spin zero fluctuations of the space-time, right? So the fluctuations that have no features in terms of it just goes up and down, right? And then there's a part of the space-time that, encode the gravitational waves. So what's the lesson here? If you do this, you must do this. You can't just perturb one part of the metric and the other part doesn't. If you do one, you must do the other. And so this, doing theories of inflation, comes for free. If you create a quantum fluctuation of the scalar field of the so-called curvature perturbation, so too must the gravitational wave be excited. And I used to always ask the question when Slava Mukhanov used to visit us. So Slava was the one that was responsible for repackaging this in a nice way. And I always want to ask Slava this question, but I was always afraid to ask him, right? Because right, exactly. So I didn't want to ask the question. The question was, we use this to make observational contact with the CMB. And this comes along for the ride, and the name of the business was to look for the B-mode polarizations. This is the B-mode polarization, right? We want to look for, but why did nature create these things and then use it? I would like to think that nature is very economical. Unless nature, is functioning like a nation state. That's a bad pun. I was going to go further with my pun and talk about inflation, but I'm not going to do that. But the point here is that so the question I want to ask y'all is, does nature make use of the gravitational waves that inflation produces? And the answer I'm going to supply to you is yes, according to this picture. And I'm going to give away the answer. The answer is that if these gravitational waves are chiral, then nature could perhaps use it to do baryogenesis. How do we show that that works? Well, the first thing I want to show you is that, my postdoc advisor, Michael Peskinos, once tell me that pretty much everything we learn about in quantum field theory is a presentation of coupled harmonic oscillators. Okay. I think he was just pulling my leg to just make me feel like I was worth something. That's supposed to be a joke, by the way. All right, so I want you to ignore this part of my equation. And I want you to think about this as, this is nothing more than the equation of a spring, right? I have this, and I want to think about this as like, the spring coupling piece, right? K is, I imagine I have a whole bunch of coupled spring, and K will correspond to, a spring of a given wavelength. The spring of a given, yeah. Okay. So this is basically an equation that represents a Fourier mode of a spring. And you might recognize this thing that if this was like some, constant here, right? This is like a damped spring. But depending on the sign, this could be an overdamped spring versus an underdamped spring. So far, so good. All right. But imagine I want to quantize my spring. Then what I have to do is to make this into a Hamiltonian. So I do a canonical quantization, and I have to rewrite it in terms of A and A dagger. And if I do this, this gets repackaged where it's a spring with a time-dependent frequency. So now I have a spring, that's a time-dependent frequency. And if I quantize that, that becomes the equation of a squeezed harmonic oscillator. So gravitational waves, what inflation does, it takes these gravitational waves and turns these gravitons into squeeze oscillators. Okay, so these waves are created in the Bunch-Davies vacuum, and as they evolve, they get squeezed and amplified, and they all get the same phase. And it's because of this phase coherence that gravitational waves become amplified during inflation. So this inflation has this magic, okay, of making use of this time-dependent background to actually do this quantum squeezing. And this is very important for what we want to do for baryogenesis. Because what we're going to do now is figure out how to piggyback ride off this type of physics. But before we do that, let me just digress and talk a little bit about baryogenesis and what it is. So what we want at the end of the day is to produce more baryons in our universe, more quarks and protons and neutrons. But you can do two ways. You can produce more leptons, more neutrinos over antineutrinos, for example, electrons over anti-electrons in the early universe. And you can use a standard model to interconvert those leptons into baryons. Okay? So if I produce a net lepton asymmetry in the early universe, at the electroweak epoch in the early universe, it will get converted. All right? I think the equation is something like the baryon asymmetry is equal to 3/11 the lepton asymmetry. This factor may or may not be correct. So the point here is very simple. What is baryogenesis? So it's an observational fact. It isn't the statement that there simply is more matter over antimatter in the universe. It's a statement about a number that we have to explain with theory. So the zeroth level statement is that the universe is dominated with matter over antimatter. Last time I gave this talk, someone very cleverly asked me, how do we know whether or not there are anti-galaxies out there? And I didn't know how to answer the question. I thought it was a nice question to ask. I just didn't know the answer. So if you know the answer, write a paper. Huh? You know what? I gave that answer, actually. I did. Okay, very good. Thank you. I'm going to write this person. Paul Davies told me it was a gamma wave background. All right, but the more precise statement is that we can measure by looking at the abundances of light elements in galaxies. It depends on a number, and it's actually this index, which is the number of baryons minus antibaryons divided by the number of photons. And that number is this thing, but it's really this 10 to the minus 10 you need. But the CMB also makes an independent measurement of this. It makes that measurement by measuring something called omega baryon, which is the number of baryons, right, divided by omega critical. So the point is that 10 to the minus 10 shows up experimentally at two different epochs. So what we need to do as theorists is to explain or post-dict this number. Right. And the point is that we don't have enough of these, we don't have the correct properties in the known physics that we have to explain this. This is going to require physics beyond the known standard theories that we have. But let's be more precise about if you were a brilliant student then you would win a Nobel Peace Prize. Okay. So Andrei Sakharov decided to not, did some great physics by figuring out the necessary conditions to, if you wanted to construct a theory of baryogenesis, these are the things you would have to do. The first thing you need to do is to have your equations, have your theory violate or basically produce baryons out of empty space. So in other words, the standard model, a way to make the statement precise is that the standard model has currents. It has, lepton currents and baryon currents. And quantum mechanically and classically, these currents are conserved according to Noether's theorem or the Ward identities. So these, yes, 15 minutes left. Oh, geez, okay. Okay, all right, so I won't get through all my talk, but that's enough. If I talk about baryogenesis, it's good enough. But you need to violate the production of baryons over antibaryons. So that's where we need charge parity violation. And notice a parity violation is important here. And this has to happen out of equilibrium, but the universe is expanding. So we hope that maybe the expansion rate of the universe is going to help you establish this. Okay. So now let's talk about, again, the important thing here is, this is the Einstein field equations in vacuum. And the theory we're going to talk about now is a theory that involves these two extra terms. And the most important part here is that you have something that looks, you probably heard about a field called the axion field, named after one of your colleagues upstairs, Frank Wilczek. And this field can have some interesting coupling to the curvature invariance of general relativity in such a way that when I look at the field equations and I boil everything down, you're just looking at left and right-handed gravitational waves, a statement of the theory being a chiral is that if this would be 0 and this would be 0, h left, the wave equation for h left and h right will be the same. But with this theory, what it does, it creates equal and opposite plus and minus signs. So what this theory does is that if it creates a kind of, what's that background when you have a permittivity, a permeable background, such that if this axion fills the universe, so if this axion was inflation, it will bias the production of more right-hand or left-handed gravity waves over the other. And that bias, the amplitude will be exponential. So if you study this theory, what you'll find is that this is a generic feature that it has. And that's going to be the upshot of what I want to say. Okay, so yes and no. It can actually be a spectator field as well. That's a good question. All right, so I think you wrote a paper with Frank some time ago using a gravitational anomaly, didn't you? Okay, so to give the answer away, remember I talked about the 3 Sakharov condition. So in the past, when people came up with these ideas, they were very clunky. You did this, you had to do this. All 3 Sakharov condition happens in one shot. So what happens is that you have this inflaton, you have inflation now, it's being sourced by this axion field. But that axion field will produce more left-handed gravitational waves than right-handed gravitational waves. That's parity violation and CP violation. I don't want to get into the details why it's also CP violated. But what happens is that the minute I produce more left versus right-handed, it sources actually more leptons over anti-leptons through something called a gravitational anomaly, which I'll say something about. But because this process is happening at a much slower rate than the rapid expansion, it's out of equilibrium. And that's the upshot of the idea. And so I'm not gonna this equation, again, the standard model tells me that a lepton current is 0, but there's this thing called a gravitational anomaly that does exist in the standard model. It's just that it's 0, because this depends on the curvature of space-time, but at the Large Hadron Collider, it's Minkowski space. So this is 0. But it turns out that during inflation, the gravitational waves themselves will source this thing And if you actually go and calculate this process doing inflation, what you find is if you do it, and I don't have, you should, where's my number? Anyway, I had a slide that basically the name of the game is to take this, integrate this over time from the beginning to end of inflation, and plug in the numbers, and you actually you could accommodate with the tuning of one parameter, 10 to the minus 10. So the upshot is that a model of inflation that already gives you the structure that we see could also, if it's happening in the context of a chiral theory of gravity, will have the ingredients to actually give you a lepton asymmetry. And so I want to end now with some recent stuff. So this is, I forget what experiment this is. Every dot corresponds to a galaxy in the sky. And then this is on the order of 1 billion galaxies. And this is recent work by Oliver Philcox and the group at Berkeley. Oliver's at the Institute now. And they basically search for parity violation by looking at collections of tetrahedral collections. So there's a tetrahedral collection of galaxies, and they can count basically. The basic point is that in 3 dimensions, if I color a tetrahedra and I perform a parity transformation, there's no rotations on that plane of reflection to take it back, right? So tetrahedral configurations can encode parity violation. And so what they did was they basically did a statistics. They counted tetrahedral configurations of galaxies, and they actually found at the order of 2.9 sigma in one case and 6 sigma parity violation in the sky. And so that's interesting. And there's a paper coming out this week by a very brilliant young postdoc, Cyril Craig Sarbanowski, Mark Kaminkowski, and myself, where we can show that actually the very same gravitational waves that are produced during inflation can actually source this 4-point correlation function. And it produces a signal that will encode this parity violation. So it's basically a 4-point function of the inflaton fluctuation mediated by the same gravitational wave. And this paper will be coming out soon. And I don't have probably like 3 minutes. 5 minutes. Okay, now I'm going to talk about dark matter. Well, everyone knows that one of the best candidates for dark matter is the axion. So I want to say a few things that the very same axion will undergo perturbations at the end of inflation. And these axions, according to the standard law, going way back to Mike Turner and others, will also form something called a superfluid dark matter candidate. And again, I want this talk to also be instructive for students as well. So we talk about things like the WIMP miracle, things like this. There's another miracle that you should pay attention to in terms of the coincidences. Another coincidence, and it's an observational one, which is that omega dark matter, the critical density of dark matter associated with dark matter measured by the CMB, divided by omega baryon, is roughly 5. So if you have a theory that can explain that coincidence, or you can use that basically to guide this. And another way of saying that is if dark matter was some type of particle that basically it ties in, basically, if you had a theory that tied this relation, had them proportional to each other. And it turns out that this axionic story can come to the rescue, but in a way that's very different. And the way that this is different is to say that the very process that is producing the lepton asymmetry, if there's a dark copy of the standard model, meaning that the standard model was completely balanced with a dark gauge theory, like SU2, SU3 cross U1, if there was this mirror standard model, you would do something what we call cogenesis, that the genesis of visible matter will coincide with the same mechanism of the genesis of dark matter. And it leads basically to a tethering of basically, by this relationship, a way to accommodate this factor of 5. And if you buy all this stuff, at the end of the day, you end up with a situation that has a following picture. That the dark matter is really a soup of axions and dark quarks. And this system will undergo gravitational collapse and form halos that have very similar semblances to gigantic dark neutron stars. So what do I mean by this? Take a neutron star and make it on the order of a kiloparsec, all right? And what does that mean? That means that this thing is dark, it's a superfluid, and its density inside is roughly a constant. And that's exactly what we need to explain dwarf galaxies. That if we look at a dark halo in our, in a vicinity of a galaxy, that basically the density basically smooths out. It doesn't spike up like the wind particles. So I don't want to get into this, but needless to say is that if we did have chirality in gravity, according to this narrative, and I'm not saying that it is the narrative, we have a way of basically tying in structure formation, baryogenesis, and perhaps maybe with a little bit more storytelling, some story about dark matter. And of course, since it's a superfluid, you would get other substructures like vortices and disk-like solitons within the galaxy that you can go looking for with gravitational lenses, and you can create problems for your grad students to work on that you are too lazy to do yourself. So, conclusion, modifying Einstein's theory in this way to have chirality can address three mysteries: the origin of matter over antimatter, dark matter, and structure formation are linked by cosmic inflation, and there are many more mysteries to be solved. Thank you.